If you get frustrated when you can't find your keys, imagine how astronomers feel. For years they've been unable to locate roughly half the atoms they think the universe must contain. Now, researchers have tracked down a lot of that missing matter using radiation from the early universe that acts a bit like a laser illuminating billowing smoke. The finding helps solidify our understanding of how the universe has evolved over time. Cosmologists know roughly how much hydrogen and helium was created during the first 20 minutes after the Big Bang. These numbers are corroborated by studies of the afterglow of the Big Bang, the so-called cosmic microwave background, CMB, which suggests that our universe is made of roughly 70% dark energy, 23% dark matter, and only 4.6% of ordinary, or baryonic, matter. However, stars and galaxies account for only about 10% of the inferred ordinary matter, and all told researchers cannot account for up to half of atoms they think should exist. This is embarrassing, as you can imagine, says astronomer Renu Sen of Princeton University, who was not involved in the new work. Not only do we have most of matter which is dark, and most of energy which is still darker, but of the 5% which is normal atoms, most are missing. Researchers think they know where the baryons are. According to the standard cosmological model, which predicts how the universe has grown and changed since its earliest days, the universe is filled with enormous strands of dark matter, and the galaxies are embedded in this so-called cosmic web. Scientists hypothesize that the missing atoms lie in diffuse clouds of highly ionized gas stretching between the galaxies. Known as warm-hot intergalactic matter, WIM, that million-degree gas glows in X-rays, but is so thin it's very hard to see. Using observatories that can see ultraviolet radiation, like the Hubble Space Telescope, astronomers have spotted enough WIM to account for about 50% to 70% of the missing baryons, still leaving a significant fraction unaccounted for. In the new work, a team from the University of Edinburgh tried to tease out the WIM in filamentary networks using an entirely different source of illumination, the CMB itself. As the universe expanded, photons in the CMB stretched to longer wavelengths and cooled to a few degrees above absolute zero in the modern day. When these photons hit electrons in the cosmic web, they can gain energy and their wavelengths shorten by a tiny amount in a phenomenon known as the Sun-Yves-Zeldovich (SZ) effect. So by looking for the SZ effect, researchers can trace the WIM in the cosmic web. The SZ effect is extraordinarily weak, shortening the photon's wavelength by about 1 part in 10 million. In order to get a strong enough signal to see it, the researchers took 1 million pairs of galaxies found in the Sloan Digital Skies survey, all separated by a similar distance, and stacked their images together. Sure enough, they were able to discern the SZ effect in the amalgamated images, providing an estimate for the amount of hot baryonic matter modifying the frigid microwave photons, as they report in a paper posted to the Arts of Preprint website on 29 September. The results suggest that matter in the cosmic web is about 6 times more dense than the universal average, enough to comprise about 30% of the missing mass. An independent study posted to ArtSciv on 15 September using the SZ technique on 260,000 galaxy pairs reached a similar conclusion. Some experts have reservations about the findings. There's some assumptions they've made that worry me, says astronomer J.